Hello everyone, Wadeduino here. Sorry for the long wait. The past few months have been really hectic for me. But I'm back and I wanted to share a project I've been working on for a long time. And though it's a bit different than the standard Arduino projects, I still hope that you enjoy it. Comment and like if you want to try this out for yourself. I would like to introduce you to my CQ Hacks 2025 project, QBrainX. So let's dive deeper into QBrainX. Essentially, this product simulates neural network functions using advanced quantum circuits to emulate brain mechanisms in ways that current computers can't. For the first feature, it uses quantum computers to design new drugs faster than traditional methods through an interactive interface web application. For the second feature, it simulates how quantum mechanics might work inside our brains to create conscientiousness with relation to neurons and synapses and its response to compounds. For feature 3, it creates a system where quantum computers and regular computers teach itself in real time, integrating quantum and classical computing for iterative learning. So the first major portion of building this project is the brain simulation, or part 1. And essentially we need 4 different files to simulate neurons and synapses and this neurological model of a brain so that we can do drug testing. It's comprised of 4 different files, the first one being the adaptive neuron learning, and this acts as an individual quantum neuron. The second one is synaptic transmission, which models the probabilistic firing of a neuron synapses. The third one is entangled neurons, where 2 neurons might be coupled and adapt over time, and it's modeling that behavior. And the fourth one is neurotransmitter decay noise, which creates synaptic noise by applying amplitude damping noise. For the first file, the adaptive quantum neuron, it essentially models a quantum neuron starting with an initial theta. The default pi/4 equals 0.785 radians. So for each epoch, the quantum circuit is simulated with optional amplitude damping noise at around 10% here, and the qubit is rotated by theta on the Rye gate and then measured multiple times where the shots equal 1000. The ratio of one measurement outcome gives the current firing probability, and theta is adjusted slightly by learning rule pushing firing probability towards the target, which is around 0.7 on the graph. And over these different epochs, theta adapts to make the firing probability approach 0.7 despite the noise. The plot shown visually shows this adaptation process, theta changing and the fire probability converging to the target. Looking at the second file now, entangled neurons, the histogram plot shows how 2 entangled neurons fire together probabilistically, affected by noise and the synaptic strength. The counts reveal the frequencies of all firing patterns measured, and the learning loop output tracks how synaptic strength data is turned to achieve a desired correlated firing rate. The plots visualize the progression of the adaptive learning process. After the loop, a plot with 2 lines, the blue line, the theta values, the synaptic strength over the steps, and the orange line, the joint firing probability over each step. And the plot shows theta increasing over time and the joint firing probability moving toward the target 0.7, and this visualizes adaptive neuroplasticity in the quantum neuron model. So now let's look at the third file, the neurotransmitter decay file. Essentially, it applies amplitude damping noise, which mimics the actual process of neurotransmitter decay in the brain that we all experience. This is commonly modeled when a neuron loses its ability to send signals properly, oftentimes due to fatigue, aging, or damage. And as the noise level increases, the neuron becomes less likely to fire, and the plots and charts show this decay visually. Now when we look at the fourth file, the synaptic transmission, it essentially simulates how real neurons and quantum systems lose energy, and it captures this kind of imperfect signal transmission, applying biological realism and quantum realism. The histogram outputted shows a visual breakdown of how many times the neuron fired versus how many times it didn't, repeated shots, so 1,000 different simulations. And it tests how effective a synapsis modeled with RY theta is under real-world-like conditions, the amplitude damping noise simulating our neurons worsening over time, and it quantifies the reliability of quantum information transmission in a brain-inspired network, modeling neural dynamics in a quantum system. Now for the second part, we aim to target the goal of drug discovery. 2 files model chemical compounds and suggest new ones, with the first file VQE bonding simulation, estimating the bonding energy of a quantum system. and the second file, Quantum GAN, generating molecular candidates and going through multi-level evaluation. For the VQE binding simulation, the VQE algorithm optimizes the parameters of the quantum circuit to find the lowest possible energy. This is important because the ground state energy tells us how stable the system is. The lower the energy is, the more stable the configuration. And this binding affinity is important because it tells us how tightly the electrons are held in a system, which is important for drug discovery, molecular stability, and quantum chemistry modeling. The next file implements a quantum GAN, which GAN standing for Generative Adversarial Network. Through each epoch, we gain insights of D-loss, G-loss, VQE penalty, as well as brain reward, which is how much the AI brain likes the molecule, as well as similarity, which is how similar the fake molecule is to real known molecules. Also generated are binary fingerprints, which is the molecule's DNA as ones and zeros, as well as bit density, VQE binding energy, which is how stable the molecule is, the brain reward, and similarity once again. Now for the QBrainX user interface, it essentially streamlines real-time data, seeing brain activity and its response to compounds while also generating molecular fingerprints and binding energy being calculated. QBrainX is so novel because it uses quantum superposition to evaluate millions of drug molecules simultaneously, quantum entanglement to model complex brain functions, and hybrid quantum classical learning to refine results in real time. This allows for faster, more accurate drug discovery and breakthroughs in simulating consciousness that classical computers cannot achieve. In relation to past approaches, classical computing, no matter how powerful, can only test molecules and simulate brain processes in a sequential order, hitting hard limits in complexity and scale. On the other hand, QBrainX uses quantum mechanics to explore vast molecular and neural possibilities all in parallel, which allows us to see solutions and patterns that were computationally unreachable before. Now let's walk through the interface of QBrainX. Okay, so here's the login and sign-up page of QBrainX. You can enter a specific email and the corresponding password, and once you log in, you'll be taken to your dashboard. So currently we are in the system controls. We can go over to the overview, and this essentially shows these 4 main statistics that we will be looking out for throughout our testing with specific drug molecules and generating new ones. We have our run history over here, and just to show you the real-time updates, we want to go to system controls, and we want to run our quantum GAN, and we want for it to generate molecules. There's also an option for you to implement your own molecules to be tested, but for this we're going to have generated molecules run and test the validity of it and how powerful and valid they are. So here you can also upload your own SMILES files. So these default parameters are pretty good, so we're going to run this. We have our live logs to the right over here, and you can see the epochs, the loss, all of it running in real time. So let's go back to our dashboard, and we can see our current epoch, our brain reward, our GAN loss, and our VQE energy, as well as our neural activity heat map. And essentially this heat map is a visualization that shows the firing patterns and the activity levels of the different brain regions during the quantum brain simulation. So if you hover over these different ones, it tells you the specific strength, and the colors correspond to the strength that it's experiencing. And you can see the system performance being modeled and it updating in real time during each of the epochs. Let's go to our brain simulation. We have our different brain metrics. We have a reward mean, which is how much the brain likes it, the standard deviation, the synaptic average, as well as the state magnitude. We also have noise injection levels and the reward signal evolution, which is basically how much the brain likes or favors the molecule from one over the other. And you can see all this being graphed and plotted in real time. So now let's go to the more important parts, the molecular generation. Once again, you can upload your own specific files, but the bulk of it are these different molecules that are being generated, their corresponding binary fingerprints, as well as their continuous fingerprints. And each of these generated molecules have statistics that one can analyze and choose the best
option given the certain constraints or goals of the project or the clinical testing. So here we can also generate different molecules, and you can see how the similarity changes as well as the binary fingerprint, and these generate each for their own specific molecule. And once we have here, we have all of these different molecules plotted with their similarity, their densities, and their corresponding molecular information that we can use for our specific goals. Now let's go to the quantum binding, or the VQE. This was specifically found in the VQE simulation file, and essentially it's giving us the energy and the ground state for binding affinity, and we can rerun VQE and modify some of these steps, and we have these converge analysis where you can see it starts to level off here. And each of these statistics are all running in real time, so you can see the latest energy and the specific convergence as well as the Hamiltonian. And this basically all stems from the system controls that you can modify and make your own. You can pause it, reset, save it, and load other one. And this is all connected to your account and email. So I hope that was a great and comprehensive review of QBrainX and each of the distinct features, from the neural activity map to the specific GAN and the epochs. And thank you for viewing my project.